Uh-huh.
Do you have copies of the Exam2 and the review work problems and the slides? She doesn't have it. I was sitting here looking at the study guide, she's like, what's that?
Okay, let me check. I usually have extras. That's the lab. This is the others. So here's chapter 3. I'm going to finish that one today. And then do chapter 4. Thank you. Y'all work problems too? Because I don't have any one of those. Yeah, the handwritten thing?
Yeah.
Okay. Not the one like wood.
Okay.
Okay. So, where was I? Wrong chapter. Here we go. Before we jump back into this, let me take that problem. Because if you're like me, it's going to be burning a hole in your brain until you get it. Right. Okay. So there, and I'll give you the details. What are we trying to do? Or just yeah.
Number 4.
Number 4.
Yeah.
And let me work from the problem itself.
Okay.
So number 4 in the review document, chapter 3, number 4. What's the mass of 4 atoms of copper in grams? Is that it? Okay. So chapter 3, number 4. So if you have 4 atoms, this is where you start from. And they're copper atoms. And we want to convert them to their mass in grams. This is a conversion factor problem. We want to end up with grams. There's no one conversion factor that'll get you from there to there. So the clue is grams. What do we know about grams and elements? We know that this value right here is grams of copper per mole. Right? So that's where we're headed, actually. We're going to have grams here and moles there to give us grams. Now we got to get from here to there. So if we've got this many atoms, what conversion factor do we know that will convert numbers of something to moles? Avogadro's number. So if we say this, and say atoms and moles on top, then that will give us cancellation for this one and that one, and cancellation for this one and that one, and leave us with grams. So we just need to know 6.022 times 10⁻³ here. And then this one is specific for copper, 6355. There. So now we know we're right because this is dimensional analysis. We keep track of our dimensions. There's atoms cancel, moles cancel. Leaves us with grams. So the rest of it is math. So that I take it that's the stumbling part. But the math is the part that's giving trouble. Once we got it set up. So we need to take this 4 and remember, this is in the numerator. So you just multiply everything across the top. 4 times this value. 2.55. So I get 254.20. Okay. Then you divide by everything that's underneath. Fortunately, we got a 1 here and a 1 here and a big number here. So we only have to divide by that number. So you just take the answer you got from the other one and say divide by, let's say I'm going to do it again. I'll touch the one button. Okay. Now we're going to divide by that number. So everybody knows how to put exponents into your calculator as a divisor. Okay. And then divide. You should get 4.22 times 10 to the minus 2.
Wait, what do you mean the exponent as a divisor? Does it, you put it in as 23 as the exponent, or do you change
Yeah,
it?
no, you don't change it. No, you put it in as this number,
Yeah,
and when you say divide, the calculator understands,
and I still get 24. I do too.
you're doing something wrong.
You can, okay, well, I need to figure out what it is, because I'll do that on
Is it an
my.
algebraic calculator? Probably. Okay, let me see if I can work this thing out. All right, we're gonna clear it first.
I need one of those. Because I think mine's wrong.
Okay. So if we say 4 times 63.55, there, equals, okay, we get the number that we talked about, 254. And then we say, whatever is in this register, we just say divide, right?
Mhm.
Why does it put divide twice?
You can hit delete and it'll take it.
There. And then you punch in this number, 4.22.
I thought it was a 6.22.
Yeah.
Excuse me, you're back. Now we need an exponent of 10. Is there a special key for that?
The 10 with the blank square, you hit 10
Right
and
down here at
then,
the bottom. X 10 times
No.
10 to the X.
22 times, and then I do this, and then I do that, and then I put my 23, and then that, and
No, that's wrong. I think we have to use this key right here.
okay.
So let's go back.
Well, that makes sense.
4 times 63.55.
Are you using this one, or are you using
Right.
that one? Yep. Oh, she's using the same key as I am.
Then you use this key. And 23.
Does that fix
That
it
is.
again? Thank you, Jesus.
That's a special scientific notation key or exponent key.
Oh, okay, well, that makes a lot more sense.
Is anybody else having that same trouble?
That's exactly what I
That was,
Yeah.
that clears up a lot of problems. Okay.
Okay, any other questions? Good. Okay, now we'll finish off chapter 3.
Well, we both are decided the same way, so that's okay.
Okay, we had come up to the place where we're gonna work a problem, this problem, and we're gonna say the conditions of the problem. We have this reaction is the basis for our calculation. We're gonna react phosphorus with oxygen. Actually, we're gonna burn phosphorus and oxygen and make P2O5. And the authors have kindly balanced the equation for you already. So if we just write the balanced equation here, it's solid, and it yields 2 P2O5. Then you can check yourself to see if it's balanced. So, 2 times 2 is 4 phosphorus here. Oops, I need a 2. That should be a 4. Okay. Just sign in and come on. And then 10 oxygens, so we're good there. Now, here comes the stoichiometry. What goes into the reaction and what comes out. Notice the question is, what mass of oxygen is required, does the phosphorus combine with? It doesn't necessarily, when you have a balanced equation, you can ask questions about just one side of the equation because the ratio is established by the coefficients. One of these plus 5 of those gives 2 of those. And we're concerned about, with this question, if we have 6.25 grams of that, how much of this is required?
So, moles.
Right, 6.25 grams. And the question is, how many grams? Mass of oxygen. So we're saying grams of oxygen. Okay? Now, there's the Great Wall. You can't get over that wall unless you're moles. Okay? So if you've got grams here, in this case, you convert it to moles of P4. And so that's a conversion factor.
Wouldn't it just be moles of P?
Well, yeah, P.
And then
But-
multiply by 4?
But yes, it's 4 times whatever P is, 30.97. Whatever that is.
120. Probably close to 1.4.
Yep, if you round it off. So that's grams per mole. Now, why do we need 4P? Because the ratio is 1 mole of that whole unit. 1 to 5 to 2. So to convert, we need 123 grams on the bottom.
Is what
Is 1 mole. And that converts, so we divide 6.25 by that. And that's 5.045 times 10 to the minus 2. Since all of our conversions are going to be multiply, divide, just keep all the decimals that you can. Right? And we'll, significant figures, we'll figure that out later. So this is moles of P4. Now that you know moles, you want to convert to oxygen. So that sounds funny. We're going to convert moles of P4 to moles of O2. But the conversion factor is the coefficient numbers.
1 to 5.
So you got 1 there, you got 5 here. Does everybody see that? You want to cancel, and this is, I did write moles, but it is moles. So moles of this now cancel, and the answer we get is actually moles of oxygen that are required to react with this much P4. So I say 5 times that, and I get 2.5, 6 times 10 to the minus 1 moles of O2.
And you just multiply that by 2. So you're going to oxygen. Because
Now this is moles of O2 because of the ratio here, 5 to 1. This is 5 moles of that unit. So this is that many moles from here, that many moles of O2.
so we're getting to grams.
Now we need to go to grams, yes. Do I need to stop for anybody? Wrinkled brows. Okay, look at it this way, the big picture. You're going from mass to moles. Then you can go from moles of this to moles of that. Then you're going from moles of that to grams of that.
How do you know you're going from mass to grams? Is that just something we're supposed to already know?
Well, no, mass is grams,
Oh, okay.
right? You're doing this unit of mass to moles of this. And then you convert moles of that to moles of this using your coefficients. Then you take moles of this and convert it back to grams.
Okay,
of
so
that.
let me ask a question so I know that I'm on the right track.
Okay.
So the way that we got that 123 is we took the 4
Mhm.
and we multiplied it by its atomic number.
Atomic weight
Atomic weight.
or molar mass.
The longer number on the bottom.
Yes.
That, okay.
Yeah, this is grams per mole of P, and this is grams per mole of P4.
So that's basically just 4.
Yeah.
Okay. Now, how did you do the 1 mole over the 123?
This one,
Yes.
Well-
Did you divide that or?
I just flipped it. When you have a ratio like this,
Mhm.
so many grams per mole,
Mhm.
as a conversion factor, it's just as valid if you need it to use it 1 mole for 123 grams. Because that was the first thing we went over in chapter 1 or 2, I can't remember which. What is this equal to? All conversion factors are equal to 1, right? Because this is equal to that. So this ratio is, if that's equal to that, then the ratio is 1. So that means that if this is 1, then you can flip it, it's still 1. But we needed the grams on the bottom to cancel the grams here on the top. That's why we inverted it, put the grams on the bottom. And when you do that, grams cancel and leave you with moles of P4. Like moles of P4. Right, we're up at this point now. Now we're going to convert to moles of O2. That's what this does. And this is based on the ratio of coefficients. That's why you can't do stoichiometry until your equation is balanced.
Technically, everything is a fraction when it divides with 1.
Every whole number has a divisor of 1, yes. Every whole number is in the numerator. Yep. So when we multiply that, we cancel moles of P4 and leaves us with moles of O2. Now we're over here. Now we just need to convert moles of O2 back to mass. And if you look at where you are and where you need to be, we need to be here. That means grams has to be on top, moles has to be on the bottom in order to cancel. Anytime you see grams and moles as a quotient, think molar mass. So O2 would be 2 times 16 would be 32. Okay, so 32 times that number is 8.07. Rounded off to 3 significant figures.
So there are actually more grams of oxygen in that reaction than phosphorus.
Mhm.
That is interesting because that means that a lot of volume of oxygen is burned.
Oh yeah, it takes a lot. And see, that was the problem that chemists were having in 1865 when they met at Karlsruhe. All they knew was mass, so they couldn't make the jump from here to here
They couldn't understand why.
because it's numbers that are reacting, not masses.
Okay, so they couldn't understand why it was taking up so much space
In this example, yep.
to make that.
Oh, no.
There we go.
Last one more question.
Sure.
How did you get the 5.045?
This one,
Yes. What was your math? Like, what math did you do
Here.
to get to that point?
6.25 divided by,
Divided, okay.
right, because this is on the bottom and this is on the top.
Okay.
Some of my students like the picket fence version,
Mhm.
where you say 6.25 grams,
And then you put
and then you do 1 mole here and 123 and 8 grams here. And that's fine. I mean, if that fits in your brain better, do it that way.
Yeah.
I use parentheses. You can use a picket fence if you want.
So how did you get the, like, we're getting 0.05045?
Because I'm multiplying the 5.045 blah, blah, over, multiplying
That's
with
standard
5.
notation. This is scientific notation. yours is not configured to give you an answer in scientific notation.
So I need
You
to
need
change something.
You need to get your user's manual and figure out how to set it up for scientific notation.
Because that is 0.005,
Yeah.
And easy way to figure out scientific notation is just take it, make sure the decimal is in the first, is behind the first whole number, and whatever numbers you take off is the exponent for the 10. So
Right.
say,
If it's -2, you go this way. If it's positive, you go that way.
so if you like take off 2 zeros, that's 10 to the second. If you take off 3 zeros from the right, that's 10 to the -3rd.
Is it always going to be 10?
No,
It's always gonna be
and we can convert it ourselves, like if we want to change it from 2.
It's going to be something times 10 to a power.
Okay,
Always.
so I can figure that out. I was like, well, we need to do but okay, I know how to do
Okay. I'm going to have to skip this one because we're going to run out of time. But it's there. Just review it and see if you have a question like that in your review document. Then we can talk about it next week during our review session. We need to get on to limiting reactants. So the concept of limiting reactant is just coming to grips with reality. Up to this point, when we balanced an equation, we were assuming exact, what we call stoichiometric ratios. That is, when we say 1 P4 and 5 O2s, that's exactly 1 mole of P4 reacts with exactly 5 moles of O2. Right? That's a stoichiometric ratio, but it never happens. In the real world, if you measure out 6.25 grams of P4 and you think you've measured out 8.07 grams of oxygen, the chances of getting exactly 807 are nil. Experimental error will throw you off every time. So one of them is limiting. That is, one of them runs out first. It just depends on which one is in excess. Whenever you have a limiting reactant, the other one is always excess. That if you have 2 reactants. So, how do we determine that? Well, this is our stoichiometric mixture for nitrogen plus hydrogen yields ammonia, your classical Haber reaction. And notice that for each nitrogen, that's the big one, we have 3 oxygen, hydrogen, excuse me, 3 hydrogens, 1 nitrogen, just like this 1 and 3. And each one has a dance, this one has 3 dance partners. Each one of these shares that dance partner. That's a stoichiometric mixture, and you end up with 2 of these each, and nothing left over. But in reality, you might have something like this, right? These 2 nitrogens get left out. They got nobody to dance with. So these 3 belong to that one, these 3 to that one, these 3 to that one. These guys are excess. Nitrogen in this case is excess, hydrogen is limiting. So when you run out of hydrogen, when they react here, 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 and here, the reaction is done. And you have left, this is all theoretical. So, I might skip this too because we're going to run out of time. How do you do this in terms of a given reaction? You know, how do you know? Well, let's see. No, that's not the one I want. Let's take an example. Okay, let's go back to the reaction we had before. I'm going to leave out the states because they just get in the way. say we still have 6.25 grams of that. And we know the stoichiometric amount is 8.07 grams. That's where they exactly match one another. If we say, all right, we're gonna put this much P4 in an enclosed vessel, a very strong enclosed vessel, because this is an extremely exothermic reaction. And then we're gonna put in here 10 grams of oxygen. Which one's limited? Well, we know that we need 8.07 grams of oxygen. Which one's going to run out first? Well, as soon as 8.07 grams of this is used up, all of that's used up. So in this scenario, this one's limited. And this one is in excess. Okay? But if we chose, say, a different amount, say we choose 5 grams of this, we know we need 8 grams of that to use up all this. So that's stoichiometric. That means this one runs out first. So now that one's limiting. And this one is in excess. It's always the one that runs out first that's limited. Let's see. Okay. Done? Yeah. Okay. All right. So we're going to have to leave this topic for now and get this last topic in before we go to chapter 4. Otherwise, we're going to be going to run out of time and won't be able to get in the lab. We're not going to postpone it a second time. It's 2045. Okay, so this last concept is the concept of percent yield. It's actually really simple. Picture yourself as a chemical engineer, and you work for a company, and the process that you're in charge of produces, it goes from this to that, so reactant to product. This costs you money, and whatever you have to do in here costs you money, or costs your company money. So the more of this that you can convert to B, the better you are off with cost benefit. So if only half of that, if you're expecting a certain amount over here, and you only get half of what you expect, then that's 50% yield. Right? The theoretical amount of B is the stoichiometric amount. So if we started off with 6.25 grams of P4 and it produced P2O5, we could calculate how many grams that would be. Right? You could say 6.025, use the same procedure as with oxygen, we use it with the P2O5. It's just a different conversion factor. And we know the stoichiometric amount, right? That's 100%. But if you actually measure how much you get after the reaction, and you only get, say, let's just, for argument's sake, say you're supposed to get 10 grams. You only get 5 grams. That's 50% yield. And for some reactions, that's good, you know, and your bosses are happy. But sometimes the reaction should be getting 85%. If you know that the reaction, the way you set it up is supposed to be getting 85%, and you only get 50%, then your bosses are screaming at you. breathing down your neck, saying, fix it, okay? All right, so the calculation itself is just percent yield is what is the theoretical amount that's based on the stoichiometry only. And then the actual amount is the amount that you measure at the end. What do you get? Times 100. That's it. It's simple calculation. Now, what does that mean in terms of, that arrow is supposed to be up here. What does that mean in terms of calculations? Well, if we go and use, we're going to use P4, but this time we're going to react it with fluorine gas. This is highly exothermic too. Yeah, big time. So P4 plus 6 fluorine yields 4PF3. We want to know what mass of P4 do we need to start with to produce 85 grams of this actual. That's the actual amount that we want. And we know the reaction is going to give us, it's based upon a yield of 64.9%. Okay, so let's see, 85. Yep. So that's all the information we need. The question is, how much of this do we actually need to start with to give us this amount? So the question becomes, can you use this in the calculation to find out that? If you use this and convert it to moles, and then go over here, how many moles does it make that's required here? Convert that to mass. Then you're going to get a number. But if you take that number and you go back over here and say, what value are you going to get over there if you use that number? You're going to get the stoichiometric value. Then 64% of that is going to be less than this. Right, see the problem? So what you have to do is find out what is the theoretical amount here. Then you can go back to there. So the theoretical amount is in terms of, you're going to convert 85 grams actual. Right? And the yield is going to be, this is 64.9 grams per 100, right? Parts per 100. So this is the yield, this is actual, 64.9 grams actual for every 100, that's theoretical. Yeah, that's right. 100 or 100 grams theoretical. Here we go. Now, the other way to do that is divide by 0.649, right, which is the same thing as what we do here. But this shows you the units that are involved. So if this is actual, this ratio is actual per theoretical. And remember, that's still a conversion factor. It's equal to 1, so you can flip it. And that cancels this one. Divide this into this times 100. And then you get the stoichiometric value of this that you can use to work back to that. Okay? So 85, 130.97.
Quite a lot of grams.
Yeah, that's a lot. So this is our starting point for calculating that. Then this has to go to moles of that, and then to moles of this, and then to grams of that. And that will give you the answer.
Because apparently P4 is limited here.
Well, actually, we're not talking about limiting in this case.
Okay.
Right? Does it say excess?
No.
It doesn't say excess. Okay. So we have to make an assumption. We don't know how much this is. But once we find out how much of this is required to give us actual that amount, then we can work from here and say, okay, stoichiometric amount will be this. And if we're focused on this producing that, we want to make this excess. So once you know how much of this you need stoichiometrically, you can bump it up to be sure that you've got plenty. Okay. Oh, I forgot, I do have the calculations in here. So you can take a gander at those too. At your leisure. But now, we need to get on to the next chapter. Chapter 4. Yeah. Fourth chapter.
Okay, so this is going to be
4. And this is something solution stoichiometry. Solution stoichiometry. And types of reaction. Okay. So let me call that one up.
let's see, we're going to close this. That one up. So we must have some videos in it. Otherwise, it wouldn't ask you for that. Okay. So how many slides? 3.
Means I gotta do better than 1 minute. Yeah, gonna do that.
You could, but we can't.
All right. Fortunately, we have a built-in review day. And of course, you can go back and look at this recording afterwards if you want. Okay. When we're talking about solution chemistry, we're going to focus primarily on, actually exclusively on aqueous solutions. Okay. Because if you use a different type of solvent, then you've got a different discussion as to the chemistry that can be done in that solution. So, and especially since most of your MLT, right? Several years I'll have A&P students, nursing students, and then we'll make reference to living systems. But a lot of reactions in MLT are going to be aqueous too. Actually, it's cheaper to do it that way if you can. But characteristics of water are paramount in understanding a solvent.
They're also very weird.
The water is actually a bent molecule. When you look at the structure of the molecule itself, there's oxygen and 2 hydrogens. And they're not opposite one another, they're kind of angled. And what that does is, we have this concept called dipole. It's not an actual transfer of electrons, it's a shift in electron density. So you get more, the electrons spend more of their time around the oxygen because it has a stronger pull. So we use this symbol, that, to show the dipole on the bond itself. So any electron density in this bond spends more time here, and this one more time there. So what that gives you is a slight negative charge. It's going to be balanced. And this is the Greek letter delta, the small delta, not the big delta. This is the big delta. That's the small delta. And it just means a slight difference in charge. Right? So this is slightly negative, and this side is slightly positive. That makes water a polar molecule. And because of that polarity, it likes particularly either ionic or polar molecules. Any of the molecules that have a similar situation with an uneven distribution of charge will be attracted to one another. In pure water, you're going to have something like this. So we know this one is slightly negative, so it makes a bond. This is actually a hydrogen bond. But it doesn't have to be. If you put some table salt in there, then you would have chlorine, because chlorine is negative. The chlorine would be associated here, and the sodium would be associated there. So the polarity of water is key to understanding how it, the proper term is solvates, how it solvates the solute.
An ionic solid dissolves in water because of its polar nature. Notice how water molecules become attached to the ions of a sodium chloride crystal in the process called hydration. Positively charged sodium ions attract the partial negative charge of the oxygen in water. A similar attraction occurs between negatively charged chloride ions and the hydrogen atoms, which have a partial positive charge. These interactions loosen the attractions between the ions in the crystal, dislodging them from the crystal. Additional water molecules surround the released ions, insulating them from attraction to other ions.
All right, so we know the forces holding this crystal, sodium chloride crystal, are very high, very strong ionic forces. They're not as strong as covalent forces, but they're pretty strong. We know that because you have to get them real hot to melt them, to break those bonds. So the forces that are being applied to these individual ions are pretty high, simply due to the hydration effect, the water attracted to the ions and pulling them apart. Okay, terminology. I used these terms already. I guess I should define them. The solute is the substance being dissolved, in this case, sodium chloride. And it's usually the minor component, the smaller amount, whereas the solvent is the larger amount and the substance that is doing the dissolving.
Is mercury solvent?
Mercury,
Yeah.
it can be.
I'm just
Yeah,
wondering, is it,
if there's more mercury than there is whatever you put in it.
yes, but does it like dissolve things like water? Is water the only thing that does that? The only liquid that does that?
I don't think mercury is particularly soluble in water.
I-
Most metals,
I was thinking, does mercury, like water, have tendency to dissolve things in it?
not particularly.
Okay.
The reason being that the cohesive forces between the mercury atoms are very high,
Okay.
even though it's a liquid. So they don't like interlopers.
So water's the only like liquid.
But you can form alloys, liquefy some metal and mix it with mercury. Your dentist used to do it more than they do now. Now they use composites, but they used to make mercury silver amalgam, which is a mixture of mercury and silver. And they use mercury because it I don't know if it makes a solution or it just facilitates the mixing of the silver, the fine particles of silver, until you get them packed in your cavity. But there are exceptions. If you start off with water and you start dissolving table sugar in it, you'll reach a point where you actually have more sugar than you do water, because sugar is extremely soluble, very soluble in water. But I don't want to digress too far on that one. But we still consider the starting point. Sugar was first as a solute, water was first as a solvent, so we continue to say that, even though we may reach a point where there's more sugar than there is water. Solvent, solute. Electrolytes. They're a class of solute that forms ions when they go into solution. And that explains why you can pass an electric current through an aqueous solution of an electrolyte like sodium chloride, because you have the mobile ions. You can't pass a current through anything that has nothing to carry the charge.
So pure water does not facilitate a current?
No.
That is interesting.
Not unless you get the voltage extremely high. And if you do that, then you actually ionize the water and then you get the current. But at reasonable voltages, water is an insulator, as is the cube of salt is also an insulator, because those ions are locked in place, they won't move. You have to melt the sodium chloride crystal or dissolve it in water.
And that's what happened to Chernobyl. It melted.
Okay, then we make a distinction between strong electrolytes and weak electrolytes. Strong electrolytes are those that are virtually completely dissociated into ions, like sodium chloride, in solution, and they'll carry a charge. In fact, they'll carry a large current. Weak electrolytes are those that dissociate slightly, like acetic acid, vinegar. It only dissociates very little bit. It'll still carry a charge and light a light bulb if you've got one in your circuit, but it's very weak when you do that. Then there are non-electrolytes, like table sugar. They don't ionize at all. They go into solution, but they don't form ions, so they can't carry a charge. Okay. Those are non-electrolytes. And these are operational definitions. You can make them what you want within reason. Oh, I guess I have to activate this one myself. Strong electrolyte.
Strong electrolytes dissociate completely to give ions in solution that conduct electrical current. Soluble salts, strong acids, and strong bases act as strong electrolytes in solution.
Okay. Weak electrolytes.
Weak electrolytes dissociate to a small extent to give only a few ions in solution available to conduct electrical current. Weak acids and bases are the most common weak electrolytes.
Acetic acid, which is vinegar. Well, 5% weight volume is vinegar. The non-electrolytes.
Non-electrolytes are molecular species that do not dissociate into ions in solution. There are no ions available to conduct electrical current. Molecular compounds like alcohols and sugars are examples of non-electrolytes.
Okay. There we go. So we need to shift our thinking just a little bit. When we were talking earlier about balancing equations and stoichiometry of reactants to products, we were focused primarily on either gases or solids. Now we're going to look at solutions. You still have reactions in solutions, but the stoichiometry, actually the stoichiometry is the same. Once you have the balanced equation, what you need to know is, besides what's the nature of the reaction, and you'll be defining that with a balanced equation, you need to know the amount of each of the reactants present. And with a solution, the amount is not defined by mass. The amount is defined by two terms. What's the concentration of your solute, because that's the reacting species predominantly. What's the concentration and what's the volume? Because with the concentration and volume, you can tell how much is being reacted. Okay, we'll look at examples. I hope we have time. But we need to, like I said, we need to know how to express the concentration. And there are several ways to do it. One of the most popular is molarity. A big M means molar. And that refers to the number of moles, and N without the zero. With the little zero here, it's what? Neutrons, right? Okay. Without the zero, it means moles. Little n means moles. And then per unit volume, and for molarity, the unit of volume has to be liters. Right? So moles per liter is molarity. So if you're ever doing a unit conversion, or you need to use this formula, just recognize that molarity is always moles per liter. Okay, so if we have 6 moles of HCl, we dissolve it in 2 liters of solution, we have a 3 molar hydrochloric acid solution. And by the way, this volume is of the total solution, not just the water that you put it into. It's the solution after you've dissolved the solute in it. So if you have, if you're going to make up a certain molarity solution, you need moles per liter. Liters, that's easy to measure. We have volumetric glassware that'll do that for us. But we don't have anything that'll measure in moles. Like our balances measure in mass, grams. So you have to convert. Right? If you've got 500 grams of potassium phosphate, you've got to convert that to moles of potassium phosphate before you can apply this formula. So how do you do that? Well, we know the mass in this case is 500 grams, but we're given the name potassium phosphate, right? That's why you needed to learn how to learn nomenclature. Because if it says potassium phosphate, you can't calculate the molar mass, not from the name. You need the formula. So we know we got potassium, and phosphate is a polyatomic ion. Look up in your table. It's PO4, and it's going to have a 3- charge, and this is going to have a 1+ charge, because that's an alkaline metal, always 1+. But this is always 3-. Polyatomic ions are fixed charge. And this group has 3 minuses. This ion would only have 1+, so we need 3 of them to balance the charge. Now we have our formula, K3PO4. Now to convert 500 grams to moles, you need the molar mass of K3PO4. Right, here it is. You just say 3 potassiums, 1 phosphorus, and 4 oxygens, add them together, and you get this number, 212.27 grams per mole. And notice that we have to put it in the denominator like we did before to make the number of moles. So the grams divide into grams, cancel, leaves us with moles. And that's the number of moles of K3PO4 that you have. And the final solution volume is 1.5 liters. So now, from that point, it's simply using this formula, moles per volume, 1.57 molar. Okay? Now, like any formula, even if the problem says you have a molarity of solution, and it says you take this volume of it, you can say how many moles of the solute are there. You just rearrange the equation, right? If this is your unknown, you just be sure this is on one side and those are on the other. It's like any equation. If you have values for every variable except for one, you can solve for that one. Okay.
It's algebra.
Right. So if we have a solution that dissociates in water, like the K3PO4, we'll use this one since it's on the slide. If we have calculated 0.25 molar calcium chloride, we want to know what's the concentration of calcium ions. Well, notice that for every mole, actually for every molarity of calcium chloride, you have 1 molarity of calcium ions because there's only 1 in the molecule. Right? So the concentration of calcium ions when it goes into solution is 0.25 molar, same as the molecule. But when the chloride breaks up into solution, you get 2 for every 1. So the actual concentration of chloride ions is 0.5. It's twice that amount.
So coefficients.
So the subscript tells you how many there are. Right? Well, this equation tells you that that breaks up into this. So you have 2 chlorides. So you've got twice the concentration of chlorides as you do calcium chloride. that you calculated. Now, if you want to know what's the concentration of ions, if it doesn't say which ions, it just says ions, then you add them together, right? You've got 0.25 molar of this and 0.5 molar of that, you have 0.75 molar ions. Now that's important to know, especially if you're going to inject something into a patient.
You don't want to have too much or too little.
You want to have isotonic solution, and if the injectable contains dissociable compounds like this, ionizable compounds, then you have to take into consideration the fact that if you think you have a 0.01 mole or something, but it dissociates into 3 different ions, you actually have 0.03 molar, right? So you could inject a hypertonic solution into your patient if you're not careful.
Maybe don't do it less.
Oh, yeah, right. Okay, particularly if there are these ions, potassium, magnesium, calcium,
So
they'll affect the nerve conduction and muscle function. Does anybody have A and P in here? A and P, okay, so you know about the sodium potassium ion pumps for nerve cells and muscle cells. Plus there's the, I think it's the calcium is part of the muscle action. Right, so all of those come into play. All right. So I'm gonna have to breeze over this and just give you an overview. If you have a problem, the question in this one is, what's the greatest number of ions? So you need to calculate the number of ions. We need to rearrange this to find out this, right?
well, the last one.
So if we take this one and convert that to liters, right? 400 milliliters is 0.4 liters, right? Move 3 places to the left to give you liters, times this. Then you get a value for sodium chloride. But when you do, the number of ions is actually twice that, because sodium and chlorine break up into ions. Do the same thing for this one. Molarity times volume, and this has to be in liters. And now you're times 3 for calcium chloride. For iron 3 chloride, it's times 4. Right? Because you've got 1 iron 3 ion and 3 chloride ions. And sucrose is 0, because it doesn't form ions. That was a trick question. So then, once you've done that calculation, you've done this one, then times its factor, then you can compare the number of ions in moles. And if you do the calculations, you'll get that as the greatest number of ions. So when you go in the lab, well, for MLT, most of the stuff you're going to deal with is prepackaged. All you have to do is know where to put what and run the instrument for the most part. There's some things that you have to do by hand, if it involves microscopy, maybe. But for the chemistry part, everything's going to be prepackaged for the instrument. Right? But if you're in research like I was, and you have to do lots of analyses, we do soil extractions, for instance, with a particular type of concentration of solution. You don't want to have to make out that dilute solution in massive quantities every time you want to run it. So, because some of those salts that you put in solution, they go into solution, yeah, but it takes them a while. And sometimes you have to heat them up to get them into solution. But you can't use a hot solution on your sample, so you have to let them cool back down. So what we do is we make a concentrated stock solution. Right? And it will be at some concentration, so concentrated molarity. And when we get ready to use it, we just dilute it. Right? So we're going to dilute it to that concentration. Right? So we take out a certain amount of the concentrated one and we dilute it to a new volume. Okay? And that's the ratio. M1V1 equals M2V2 is the same as M concentrated, volume concentrated equals molarity dilute times volume dilute. Okay. So when you have a problem where you're going to do a dilution, what you need to do is like almost every other problem we work, take the word problem and pull out the information and set it equal to your variables, right? Equals something. So that you are sure that you get it in the right place in the formula. If you don't do that, then you could plug it in the wrong place, and of course you get the wrong answer. I wish I had time to go through the theory of that, but unfortunately we don't have that time. This is a good explanation. Right. So just run that, and it shows you that when you pull out a certain volume of the concentrated one, what do you have? You got the volume, but you also have a fixed number of moles of the solute. Now, the moles of solute that you start with is the same moles that you end up with. Right? So M1V1 equals N, number of moles, and M2V2 equals that same number of moles, because the number of moles that you took out doesn't change. Whether it's here, take out, put it over here, same number of moles. So that's why M1V1 equals M2V2. That's this, what's that called? The cumulative property. A is equal to B, and B is equal to C, then A is equal to C. Okay. All right, I'm down to, I want to be sure I get, all right, we're going to have to, sorry, we have to blast through this one. That's just what I told you. Lay everything out and make sure you've got what's your unknown, what values are you given. Then you can use the formula. Okay, types of reactions. We can divide reactions into certain types, and they will fit in these categories that I haven't explained yet. But one reaction could be multiple types. You could have an oxidation reduction reaction, which is also a double displacement or a combustion. It could be multiple types. Yeah. So we just need to define what they are. Precipitation reaction is one where you put two solutions together, and they are in solution, right? You can see through them, shine a light through them, and you can't see the beam. Put those two solutions together, and you make a solid. That's a precipitate. Just drops out a solution. It may take a while, right? But it'll eventually settle out. Acid-base reactions. Acid bases are where you have some acid here, a generic acid, and then you react it with a base. So the acid will have a proton here and a hydroxyl here. You'll combine these two together, and these two then combine to H2O. So this will be your acid, this is your base. This is by definition a salt. Combination of an acid and base produces a salt of the ions, the cation and anion,
So
plus water.
and sodium hydroxyl.
Yeah, hydrochloric acid, sodium hydroxide makes sodium chloride plus water. That's an acid-base reaction.
You really don't want to be in a room with that reaction though.
Yeah, well, it depends on the concentration. It is exothermic, yes. Most acid-base reactions are exothermic. Oxidation reduction. All right. We often abbreviate redox. So an oxidation reduction is one in which electrons are transferred. That's it. That's the basic definition. During a reaction, electrons from one of the reactants are transferred to the other reactant to produce products. A combination reaction is one in which two elements produce a compound. So you put sodium metal and chlorine gas together, you get sodium chloride and lots of heat.
Oh, that would not be a good idea.
Decomposition is just the reverse. You take sodium chloride and you drive an electric current through it, you can separate it into sodium metal and chlorine gas. So they're opposites of one another. Combination is an opposite of decomposition. Single displacement is where you have a compound and an element, and the element replaces one of the components here. So let's say this is a metal. Right? So this is our cation, this is our anion, this is going to replace A. So you have Cb plus A. Okay? Or for a real example, zinc and hydrochloric acid, you'll get zinc chloride plus hydrogen gas. Now, that's not balanced, but the reactants are correct and the products are correct. So this zinc replaces that hydrogen. Interesting fact about this one is, if you have an element on one side of your equation, no matter which side, and it ends up in a compound on the other side, you also have oxidation reduction. Okay. Double replacement. So if we have, well, generically speaking, we have a compound, cation, anion, cation, anion. You just swap the cations. So we have a Cb plus an Ad. So you have two compounds, and you swap components. That's a double replacement. Then a combustion is anything plus oxygen.
Little fire.
Usually, yeah. So we can say in the space shuttle engine, it will be hydrogen plus oxygen, just water. That's a combustion. Combustions are also redox reactions. And it follows that same rule. You got an element here, that oxygen ends up in a compound. That's a redox. Okay, so precipitation reaction is also a type of double replacement. So in that case, this will be a solution, and we write AQ for aqueous. And then maybe this one turns out still in solution, but this one makes a solid, drops out of solution. So that precipitation reaction is a double replacement also. There's an example. And
Silver ions.
sorry, don't have time for that. When we say soluble, these are relative terms. And that's going to be good enough for now. We're saying that a solid dissolves in solution, and in this case, we're talking about aqueous solutions. Or a solid does not dissolve in a solution, like our precipitate, or if you put something in water and it never goes into solution, then it's insoluble. And for now, slightly soluble and insoluble are synonymous. Because we'll find out later that everything that you put in water is soluble to a certain extent.
We take some of it.
It may be just the smallest amount. But for now, we have a difference between soluble and insoluble.
You cannot find.
And there's that table in your review document. Look on the back. I think it's the last page, actually. Yeah, review document. Is that it? Yeah, the last one where it's got those grayed out squares. If you want to find out whether a cation and an anion together are soluble in water, you just look at the cation across the top, follow it down to meet the anion, and see if it's grayed out or it's not grayed out. If it's not grayed out, it's soluble. If grayed out, it's insoluble. That way you don't have to memorize the rules. Now, the rules are there on the page, but I'm not going to make you memorize them. If you were a chemistry student, yeah, you'd have to memorize them. Okay, so these are the simple rules for solubility. And we're going to have to. All right. You're also going to have problems in your review document that ask you to write the molecular equation. Okay, that's just the equation as we've known it from this point. Just write the molecules, balance them across. The whole thing, everything in there. Right? That's nothing special. But recognizing that where you have an AQ next to them, they're aqueous, they actually break up into ions. So if you write all the ions on the reactant side yields all the ions on the product side, and if there's a precipitate, it doesn't break up, right? It may be ions on this side, and on that side it's a solid. So it stays a solid from this equation to this equation. That's the complete ionic equation. You'll notice that, let's see, here we go. There's a complete ionic equation of silver nitrate plus sodium chloride. Silver chloride is insoluble, so the silver combined with the chlorine to make this solid. And you still got sodium and nitrate on both sides. So what that means is, if you see sodium, if you see an ion on one side, you see the same amount of that ion on the other side, you can cancel them out. And that gives you the net ionic equation. All right, so that's the net ionic equation for that reaction, right? Originally, silver was combined with nitrate, and chloride was combined with sodium. But when you combine them, you get this. And the advantage of knowing this net ionic equation is it doesn't matter what the counter ion is for silver, as long as you can get it into solution, and the chloride get it into solution, doesn't matter what its cation is, you'll get that reaction. So if you need that reaction and you go to your storage room and you find, uh-oh, I don't have silver nitrate. I may have silver acetate. You can still do the reaction. These are called, in this case, sodium and nitrate. Those are spectators. They just sit there. Right? Before and after, they're still in solution. Still ions, no reaction. So this is everything together for this reaction. This is the complete ionic. Notice that cobalt is a 2+ ion, right? And you know that because of the formula. But there's only one of them. But there are 2 chlorides that come out of that. So now this 2 subscript becomes a coefficient, because you need 2 chlorides separate from the cobalt. Right? In this case, you've got 2 sodiums. Already you've got a coefficient, so you put that one in there. And 2 hydroxyls, you put that in there. And then you leave the cobalt hydroxide alone because it's a solid. And then you cancel out the spectators. That's how you go from, this says formula equation, that's molecular equation. Well, actually, formula equation is accurate. Molecular equation is a misnomer, but I've used it so much. Just think, if I say molecular, think formula. Now, if you read formula, think molecular. Okay, so we don't have time to do that. Let's see. Titrations, when you have an acid-base reaction where you put one acid, or actually it doesn't matter, where you're combining a known amount, use a special.
It's a thing that drips.
Right. Use a special device that's numbered in reverse order. Instead of being from bottom to top, it's top to bottom. The reason is you want to measure how much was delivered. So So if you start at 0 and you deliver a certain amount, they just read it off. This is a burette. If you put something in here, let's say it's 0.1 molar sodium hydroxide. We know that exact concentration. So if we know the concentration and we know how much we delivered, we can calculate how many moles of base were added. Right? So we're going to add it to what? We're going to add it to some acid and neutralize it, right? So we need some way to tell when is the reaction complete. So we use an indicator. An indicator that changes color when we reach a certain pH. And that lets us know that the reaction is complete or close enough. And if we know the concentration, the amount delivered here, then we know the moles of base. And that will be based on the stoichiometry of the equation, and I'll have to go into that detail later. We know the moles of acid. Now that we know the moles of acid, we know that that's also equal to molarity times volume. We put a known volume in here, so then we can calculate the molarity of the acid. Okay, that's a titration. When we do one of those in the lab, we'll go into more detail about the mechanics and calculations. The difference between equivalence point and endpoint. The equivalence point is where these moles are exactly equal, right? And the only way you can tell that is to do a titration curve with a pH meter. You can't do that with every one. Let's say you have 100 titrations you need to do. You don't want to sit there and gather data on each one of those. So you do it on one of them, find out where the equivalence point is, and then you pick an indicator that will change color at that point. Then you put the color in there, and you just knock them out one after the other. Okay. That's the end point, where the indicator changes color. And you try to pick it so the end point is very close to the equivalence point. That's for your best accuracy.
So near 7 pH, next to water, because an acid is base is water.
If they're both strong. We'll have to talk about that when we get to acids and bases. Redox reactions, okay, I'm going to have to. These are the rules for assigning oxidation states. An oxidation state is kind of like a charge, but it doesn't have to be a charge. An oxidation state is a way of bookkeeping, keeping track of charges. Right? So when you assign an oxidation state in a compound, say we have potassium dichromate. There we go. The alkali metals are always one charge. That's +1. They're never anything else. Oxygens, we assume, are 2- for bookkeeping purposes. Unless they're peroxides, and then they're 1-. But for most cases, oxygen is going to be 2-. Now you know this charge, you know that charge, and the total here is 14-, right? 7 times 2-, and 2 times that is 2+. So that means you have 12-, right? Because 2+ neutralize 2-, you got 12- left over. Now you got to neutralize those 12- with the chromium. Okay, so if 2 chromiums are equal to 12+, to match that, how much is each chromium? 6. 6+. So you can calculate the oxidation state of everything in the compound with these rules. Now, if you have a free element like that, it's 0. Or if you have a metal like that, it has a 0 oxidation state.
You get the 6 by dividing the 12 by 2.
Exactly. In most compounds, hydrogen is given a 1+, fluorine is given a -1. In a compound like this, they all have to add up to 0. it's neutral. But if you have a polyatomic ion that you're looking at, say PO4 minus 3 minus, then all of the charges or oxidation states together have to add up to the charge.
An ionic compound.
Huh?
An ionic compound.
This is an ionic compound.
Oh, okay.
But if you're looking at this, say oxygen now is 2 minus, so that's 8 minus total, right? But you only need to neutralize 5 of them. Because 3, you want to save 3 charges, 3 gains. Right, so this has to be 5 pluses. Okay. You're practicing, there's plenty of practice in your review document. We can talk about it next time. So these are examples. Redox reactions. I'm sorry, we're just going to have to go past. Yeah. I will give you this, though. Let's see. Is that part of it? No, it's not in here. Okay. So how do you know the difference between oxidation and reduction? Use this acronym. Oxidation is loss. So anytime electrons are lost from a species, it's oxidation. Reduction is gain. So anytime something gains an electron, it's being reduced. Okay? These are examples. How do we know if something's being oxidized or reduced? Well, there's a quick way and a long way. If you can use the quick way, fine. Notice that if you got like I said before, if this is zinc here, it's in a compound over here, that's oxidation reduction. Right? And to find out which one is which, you need to do oxidation states. This is a pure element, so that's 0. Hydrogen is +1, chlorine is -1. Then with 2 minuses, zinc is 2 plus to balance those 2 minuses. And this is 0. So we went from 0 oxidation state, zinc, to 2 plus oxidation state. What happened? Was it oxidized or reduced? Well, how do you get a plus? You remove 2 negatives. Right? So that means you separated 2 electrons from this one, and that gave you this imbalance of 2 pluses here. So 2 minuses balances those 2 pluses. So that was, zinc in this case was oxidized. It lost electrons. And the only way to be sure is to do the oxidation states for every species in the reaction, and then see which one's oxidized, which one's reduced. Recognizing also that anytime you have an oxidation, you have to have a reduction. They always come in pairs. Okay, so here's an example, and you can run through that with your with a PowerPoint that's on Blackboard. It'll show you those animations. I'm sorry we had to go so fast. We'll take more time to review next week. Just be ready with questions. The ones that are really burning through your brain, we'll get those first. Then we need to go in the lab and do today's experiment. Everything's in there. There's enough room for 2 groups. Set up for just 2 groups. The only thing you'll have to bring with you besides your lab notebook, your exercise, and your lab coat, eyewear. If you need eyewear, then we've got that in there, and I'll pull those out for you. And you need a cord. Each group needs a cord because you're going to weigh it. If you read your method, you know that you need a cord. So let me stop this recording. Now, the